Good morning, good afternoon, good evening. Hello, everybody, currently in the present and in the future. I'm Victoria Vesna. I'm director of the Art Science Center at UCLA. And I've had the pleasure to know Walter Gekelman since I came to campus in 2000. He's always been an amazing person to talk to. And just a little bit about him. He is a plasma physics professor here at UCLA. He's an elected fellow of the American Physical Society. And he's known to have developed and constructed numerous meter-long devices to study fundamental plasma processes under laboratory conditions. The largest one is Large Plasma Device, LPD. That is a real fascination for me. I have visited his lab many times by myself with students. It's in Westwood, hidden, and once you enter, you're just entering into a whole different world. I always see Walter as an artist who's creating this crazy big sculpture that actually goes into the most amazing scales. And to hear him talk is so great. And I'm so happy that he agreed to give us a live tour. Welcome, Walter, and thank you for doing this. So just tell us a little bit about where we are and take us on a beautiful tour of your plasma lab.
Okay, thanks, Victoria. Well, we're in the hallway down a few meters away from the lab. We thought we'd start here. It's sort of quiet in here. In the lab, it's very noisy, you'll see, because there's a lot of equipment. But before we go in there, for your audience, I'd like to just say what a plasma is. First of all, it has absolutely nothing to The difference between all these substances and plasma is that plasma is so hot that the atoms have come apart and you have charged particles called ions, positively charged particles, and electrons, negatively charged particles. And so there's very little plasma on the Earth. That's why we're not familiar with it. For a moment, there'll be plasma in a lightning flash. There's a neon sign in back of me which says plasma. So what are the temperatures? There's no upper limit to plasma temperatures. So when a star explodes, it can be many billions of degrees. The coldest plasmas that one can make in the laboratory are a few thousand degrees. And when I say degrees, I always mean centigrade, okay? Now, on the Earth, people have made plasmas in fusion experiments trying to get thermonuclear fusion for energy of a couple 100 million degrees, which is extraordinarily hot. To give you an idea, the interior of the sun, which we're undergoing fusion, and that's where all our energy comes from, heat the Earth, that's about 12 million degrees. And the surface of the sun, which we see through telescopes and so on, is only 8 or 10,000 degrees. So in order to make fusion on the Earth, you can't go to 12 million degrees because a fusion reaction is really steep function of temperature. So at 12 million degrees, you would need a plasma the size of the sun, something huge, to get your money back, to get more energy out than you put in. So that's why you have to go to hundreds of millions of degrees on Earth to make the plasma put out more energy than you put in. There are a number of experiments worldwide trying to do this, of course, as a new source of energy, which, by the way, would be very, very safe. It can't explode or melt down, and there's no really horrible radioactive waste. Now, what else is plasma good for? Well, the iPhone that my photographer is holding is filled with computer chips, and every one of those was made in a plasma. So modern electronics, iPhones, smart TVs, the entire internet, anything that has a computer chip in it, your car, which has many, many CPUs, every one of those electrical components was made in a plasma, because only in a plasma do you have the control to build CPUs and so forth, atom by atom, and assemble transistors and wires and capacitors and all the things that go into electronic components. So essentially our economy, whether you know it or not, is heavily, heavily dependent on plasmas. Plasmas are used in medicine, they're used in propulsion in space. There's a huge, huge list. I can't go into all of it. What we have here at UCLA is we're studying plasmas in a machine. It's the only machine of its kind in the world. And we'll go take a look at it now, and I'll show you what all the components are. But we're studying in that some topics related to space plasmas. The entire Earth is surrounded by a plasma, which comes from the solar wind. And there are violent magnetic and electrical storms in that plasma, which can wipe out communications on the Earth. They can endanger astronauts, stuff like that. We have to understand it. And this machine's perfect for reproducing those phenomena that happen in space. But here we can control them and study them. In space, they just happen. You don't know when they're going to happen. And all you might have is a few satellites. We can also study phenomena that happens near the surface of the sun, these giant arched ropes of magnetic field, called flux ropes. And we can build them here in the Earth and then study them in great detail. We can study things like transport, how heat and energy go across magnetic fields and along magnetic fields. And all that kind of studies is relevant to fusion. The reason that you'd like to do some of that stuff here is the fusion machines are so hot inside of them that it's very, very, very difficult and very expensive to measure anything. And so here our plasmas are much colder. Instead of 100 million degrees, they're only a couple hundred thousands of degrees. And they only last for 10 or 20 thousandths of a second. So in that time and at those temperatures, we can build probes and detectors that we can stick into the plasma and measure stuff, something we can't do in a fusion machine. So there are a large number of experiments going on here. There's no way or time for me to tell you about them all. I'll show you some really pretty images that come out of the experiments, images of the data that we acquire, and I'll try to tell you how we take them. That's maybe where the art comes in, because some of them are very striking and beautiful. They're all snapshots of stuff that happens in sometimes billions of a second in these machines. So we'll take a look at that too. So let's go down the hallway to the machine. These are all posters from scientific meetings that we've attended. Of course, now there aren't any scientific meetings unless they're virtual. And so this machine is always being modified and improved, but the basic machine was finished around 2000. So this is it. Maybe you could pan over it. First thing is you can hear this huge noise. That's actually the wires jumping every time the plasma turns on. You'll be able to see that in a moment. The yellow and purple things you see going along the length of the machine are electromagnets. So there are electrical currents and that makes a magnetic field that goes down the length of the machine, constant magnetic field. You'll see these windows. You'll be able to see the plasma better. You can see it flashing through the windows. Then what we have here, these are detectors probes. This particular probe is measuring the plasma density at the moment, and they can be moved by computer. Here, you could zoom in on it, and I'll move it a little. So this ought to be moving, see? So a computer program is moving that probe. See, it just stopped. It has precision of maybe half a millimeter or a millimeter. And normally, when we take data, if we want to measure the density, this probe is programmed to go up and down and in and out in the machine. We have these special valves that we built that can move in 3D, see? They track the probe motion. And so we could typically measure the density, let's say, at a few thousand locations on a plane. And then we'll move the probe plane by plane by plane. And if we want to, we can take data throughout the entire volume of the machine. And we measure the density, we can measure how hot the plasma is, we can measure the magnetic fields, the changing magnetic fields inside the plasma, electric fields inside the plasma, currents, things like that. All the things you need to know to understand what's going on. So this thing over here doesn't look like much. Is a vacuum pump. There's 4 of them on the machine. And inside this pump are spinning blades, like a jet engine blades. They're spinning 40,000 times a minute. And that spinning action, if a particle, which bouncing them around the machine, boing, 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 goes into this tube, it gets caught in the blades and expelled from the machine. And that's how we keep a vacuum. So it's 4 of these things. The vacuum conditions are about, if we remove the gas that's making the plasma, it's about 1 billionth of atmosphere. So kind of like in space. So first we have to pump all the air out of the machine. The pumps must be on day and night. They can never shut off. The reason is that at these very low pressures, the walls and the probes and everything is evaporating all the time. There's no liquid state. They just evaporate and become gas. And that will make the vacuum contaminated and useless to make plasma in. So we're always pumping the machine. So there's all different kinds of ways of making plasmas. This particular plasma, technically it's called a DC discharge, direct current discharge. Embedded in these magnets here, and you'll see it through a window, is a hot glowing plate of a substance called lanthanum hexaboride, very fancy stuff. And you have to heat it up very hot. So right now it's about 1800 degrees centigrade. That's like 3,500 degrees Fahrenheit. And you'll see through the window, it's white hot. And when it's at that temperature, it's very easy for electrons to be removed. And then right over here, you can't see it either, is a mesh grid of molybdenum. So what we do once a second here, we make this very negative with a power supply over there. And then the electrons see a positive anode. They come rushing out in a huge stream and go from there to there, basically. But they have so much energy that they tear apart the helium gas, which is in there now, and make a plasma, which then fills the chamber. This, all the transistor switch and all the power is coming from here. You could look up there. Part of the noise are those cables jumping. Right now, the plasma current is 7,000 amperes. And so that electrical current, and then there's some stray magnetic field from the magnets, is enough to give the wires a kick. And make, so that noise is just the wires snapping like a whip. if you look in here, it's really, really bright. So that's that disk of lanthanum hexaboride, and you can see how hot it is. And then the flash that you see is light coming from the helium plasma. Maybe we go to another window. So that's the plasma, and it's completely formless. It just looks like a bright flash. And it's only on for 10 thousandths or 15 thousandths of a second right now. But many of our experiments are over in a millionth of a second. So that as far as a lot of our experiments go, the plasma lasts forever. And the way this machine was built and carefully designed is that every time the plasma flashes, it's exactly the same as it was the time before. So we can actually repeat an experiment. We have many times, millions and millions of times. So to take fully three-dimensional data, I can show you pictures of that, can sometimes take a few weeks, 24 hours a day of operation as these probes slowly move through the plasma and acquire the data. Oh, these are bottles of gas. This is where the plasma comes from. This is a tank of argon. So there are all these different tanks, so we can make plasmas out of different gases and mix them with these things called mass flow controllers. Okay. Also, the magnets use a huge amount of electricity, maybe as much as Westwood. And that power comes through those bus bars that we had to put on the walls. Ordinary wires would just melt. And so this is water-cooled copper that runs power to the magnets. There's a bar going like that. And under it, spaced by glass, is another bar going in the other direction. So the current comes and goes along the same path. But then it goes through the magnets. And all the magnets have to be cooled. See all these cooling pipes? There's a lot of water flowing through the machine, about 750 gallons a minute, cooling the walls of the machine, the magnets, and so on. And if we didn't do that, these magnets would all melt. We're going on down. This is a laser used for a scattering experiment. This is an antenna. What I didn't mention before is who's paying for all this, right? It's not dirt cheap, but it isn't ridiculously expensive. We're funded mostly by the Department of Energy and the National Science Foundation. And the reason they give us money is they made this into a national user facility for basic plasma physics. So scientists come from all over the world, most of them from the United States, from all kinds of institutions, national labs, and industry too. We work with industry. This antenna was for an experiment that industry is interested in, for example. There's also an antenna in here, you can't see it, which is for an industrial experiment. And so these folks come here, the government pays us to run the machine. So when people come here, of course, nobody's coming here now, but when they come back, and over the years they've been here, the use of the machine and our personnel, all the probes, everything is free, paid for by the government. All they have to do is pay for their airfare to come here. And then they'll work with us for a week or two on whatever experiment they're doing. There's about 20 or 25 very, very different experiments per year going on in the machine. And in this short amount of time, there's no way to explain what they all are. But anyway. These are more pumps. You look in the end, you could see the plasma source again. It looks like the sun, sort of, really, really bright. It's so bright you could hardly see the flash of the plasma. And of course, the plasma, as I said, is a couple 100,000 degrees. It's toasty, but nowhere near fusion conditions. And there's a lot of infrastructure here. I won't go into it all, but this is heat exchanger. We use a lot of water, and because California is always in drought, we can't throw any of it away. So the water gets, there's a chiller plant across the street that puts ice cold water in these white pipes over here. And that's heat exchanged with the water from the pipes of our machines. See these copper pipes. And so we transfer heat to the chiller water, and that goes back into this giant refrigerator across the street that cools it down again. That way we can have cold water running, and we don't use any water at all. And okay, this is another plasma source in this box. It's like the other one, a little bit smaller, and we could move it in so we can have plasma coming from both sides. Probably next week we're going to put it in and do some tests with it. So we'll go into the room next door because it's quiet. It's very, very noisy here. I hope you're hearing me well. But generally, after spending many hours of the day in this room, you're nice to get into a quiet spot. So this room, she's panning around it, is called a control room. Just about every machine device has a control room. And right now we're the only two people in it. Actually, for the last few months, there's only been a few of us working here. The students can't come here. One or two graduate students have come in briefly to do work on their thesis. But other than that, we usually have this place filled with students, graduates and undergrads, but they're not allowed here. And our staff, maybe half of them come in at a time, something like that. It's a real pain, but you all know about that. But it's quiet in this room, and when you're taking data, once you start a data run, it's all done by computers. They move the probes, they digitize the data, they can actually change settings on amplifiers and things like that. And so there's no need to be in the lab. So people come in here and use the internet. This is a computer program which catalogs the data as it's coming in. We're not taking data now, so you don't see anything happening. And it puts up the machine state and so forth. That's running now, but otherwise, there's not much going on in here. So Victoria asked me to show you some of the images that we come up with in our experiments that, in my opinion, I think they're really pretty, but they're all data that we acquired. So one thing is, suppose you measure data at 50,000 locations in the plasma. And at each location, you may measure the data at 20,000 different times, right? Those time steps could be a millionth of a second apart, or a fraction of a millionth of a second apart, or longer. You can decide what you want to do. So now, and so you have, and then you're measuring quantities like magnetic field or electric field. So those are fields, so they have three components, the X, Y, and Z component of the magnetic field, for example. So what you're left with is this huge, huge set of numbers, terabytes of them. And there's no way by just staring at these numbers for you to figure out what's going on. You just, your mind won't, it'll just turn to jello. So the only way to try to understand what it is you've just measured is by making an image of the data or a series of images, okay? In the form sometimes of a graph, like that's a simple graph, a 1D graph, you could just see those lines over there. Or two-dimensional or three-dimensional graphs. And once you have them, then suddenly what you're measuring comes to life. So for example, this was taken years ago. This pretty picture is actually magnetic fields. And what you have is there's a current over here, an electrical current coming out, and another electrical current over there, and then a small one over there. And these currents are moving in time. And when they move, they force magnetic fields in the center to squish into each other. And when that happens, some of the magnetic field's destroyed. It's a process called reconnection. And the magnetic field has energies. The energy has to go somewhere because energy is conserved. So it can become heat. It can become waves that come out of this region and go flooding into the plasma, for example. It can become beams of particles that go flying out, or flows. The plasma can start flowing like in a river. And so if you want to study a process like this, number one, you have to visualize it. And when you do, you can make images like this. The red means stronger magnetic fields, blue means weaker magnetic fields. And this is just one instant of time in a plane. And actually, I'll show you in a movie. Let me see, is this it? Yeah, this is the same image, just looking at it from different angles, moving around. And this is that region in the middle where reconnection's going on. You can see it's completely three-dimensional when you start looking from different angles. When you just have one view, you may be fooled to think that it isn't three-dimensional, okay, but it is. And so how do we do this? First, you have the data at all these locations and in three-dimensional space. So for example, maybe this is easier for you to visualize. Oops, come on. This is something else, a different experiment. These are three-dimensional currents of of things called magnetic ropes. Magnetic fields of these ropes. And you can see this is a birthplace of one rope, and this is the birthplace of another rope. But they're not ropes like in a fiber rope or a string. They're ropes of magnetic field. And they're created because the currents come out of these things. They have their own magnetic field. And there's a background magnetic field. And those together create this topology. This is we put a little mirror in the back so you could look at it from the other side. There's only one rope, system of ropes. That's just a different view of it. And so as time goes by, this entire sequence of images is maybe 1,000th of a second long from beginning to end. And you could see these ropes at first twist in 3 dimensions. And then when they store up a lot of energy, this reconnection happens in here, they relax and straighten out, right? And this happens again and again and again, okay? And so how to acquire this? So how did we take the data and how did we visualize it? At least I was asked to explain that. So what we did was, this is a volume. The distance from here to here, I don't remember exactly, but it's something like 5 or 6 meters. And the distance from here to here is much smaller. It's about 30 centimeters. And so, or 40. So this picture is sort of squashed in one direction to make it easier to see. Otherwise, it would really be stretched out. So what we had to do is move a probe that could measure all 3 components of the magnetic field throughout this volume. So that takes a long time. The probe moves takes data for a few seconds, then moves a millimeter, takes data again, and moves a millimeter, and so on, until you fill this volume with tens of thousands of positions and, of course, time. So now you have this huge stream of numbers. Then you have to take these numbers, and from them, you can calculate the full magnetic field. And if you start over here, you could actually follow the magnetic field, because magnetic field is represented by something called vectors. So they're like little arrows. I can show you a picture of vectors in a moment. And they just say, the bigger the vector is, the bigger the magnetic field is, and it points in the direction the magnetic field is at that position. So what you do is you have a vector here, then you go to the tip of the vector, you follow it, then you say, where's the next vector, right? Then you follow that. You keep following them, and then they will describe these orbits that you see in red and blue, okay? So now you can store these lines in a computer. Then what you have to do is you have a program that takes this line, that then takes a little circle that you put around the line and extrudes the circle, right, to make a tube, all right? And just for you to see it, because the line is so small, you wouldn't be able to see anything. So now you have this tube, and then our group wrote software to take these tubes and essentially break them up into zillions of triangles. And then in this case, we feed it to a program, commercial program called Maya. And that program understands triangles and can color them. It can ray trace, see it makes these shadows and all this stuff, and titles. And so once you have all the triangles, you can then input them into this program and make these movies frame by frame. So that's how it's done. So we had to use visualization techniques. Luckily, there are companies, and Maya's not the only one, that have software like this that allows us to take data, then you need an interface to the program, and then you can make images. It's actually a lot of fun to do. It's like doing art. Which software? Okay, well, here, I'll put up another image in the meantime. This is very striking. But you see these arrows here, see these red guys? Those are vector arrows of electric field. These yellow lines are field lines of electric field. And these things which I colored, the colors don't mean anything. I just colored them because they're pretty and easy to distinguish this from that. These are flows in the plasma measured by a different probe. And you could look at this in time. While we're talking. So essentially, first we acquire the data, and there's a special program written by a couple people in our group that actually takes voltages. Essentially, everything becomes a voltage, and then it's digitized by digitizers that change the voltage versus time into numbers. And everything's calibrated so we know this voltage corresponds to this magnetic field or that magnetic field. Okay, so then now we have all these numbers. Then to create the field lines, if you want it, one way to do it is use commercial software. One is called IDL, which is used a lot by astronomers and physicists. A lot of people here use Python. That works perfectly well to do this, and it's free. And so now you can have data sets that you can graph. And if you want to do fancy stuff like that, then we take these data sets and import them into Maya, for example, which not only will do this, but you can make two views 6 degrees apart and get stereo. So unfortunately, I can't show it to you all, but we have a stereo system, and you could look at the stuff in full 3D if you want to. So there are all kinds of interesting forms. I'm going to show you another one. But if there are any more questions or any questions at all. This is very pretty. This is called a drift wave, and this is density now, plasma density. You'll see it changing in time. Right now, this is just noise. And this was acquired some time ago, but it looks like a little spiraling galaxy. It's very pretty, right? And the drift wave, each frame is 20 microseconds, 20 millionths of a second, and the drift wave has a frequency of a kilohertz. So in 1,000th of a second, it makes one full spin. Okay, and so I don't want to talk about drift waves much, but it's pretty. Okay. Oops. I'll show maybe one more. Oh, this illustrates the arrow business. So over here, this was a sheet of electrical current, and I don't have it in the beginning. It's just completely formless sheet of current. And then after a certain amount of time, very, very short time, a few millionths of a second, it tears up. So there's a current here and a current there and a current there. It's something called the tearing mode in plasma physics. But each one of these little arrows is where data was acquired. You could see this is not very big, 20 centimeters by 30 centimeters. And this is at one instant of time. This is completely changing in time like the other stuff you saw. And we colored it so that the brighter this is, the bigger. This is, again, magnetic fields due to this tearing of the current. And so you could see all these arrows, and in your mind's eye, if you follow them around, you could get lines of magnetic field, okay? And essentially, at every one of these spatial locations, thousands of them, we took data. So a probe went over here. It stored maybe 10 or 15 shots of the machine, then moved to the next location and did it again and again and again. So this is only can be done by robot probes. I mean, you'd never want to do this by hand. You'd go crazy. And so you need all the modern tools in a lab like that, like computer-controlled stepping motors and data acquisition systems that enable you to do this. And they're in vogue. Many, many places now have them.
We have another question.
Okay.
How dense are plasmas compared to solid matter?
Oh, okay. They can be, these plasmas are very, very tenuous. So for example, that big machine you saw in the other room, there's probably as much helium in that machine as there is air in your nose. Very, very, very little. So plasma is very, very tenuous. It's about 10 to the 13th particles per cubic centimeter, and solid density is about 10 to the 22 particles. So it's about 1 billion times less dense than a solid. But laser-produced plasmas, they're trying to get fusion now by firing multiple laser beams, hitting a target and compressing it and heating it. And they want to heat it to a couple 100 million degrees. There's a big experiment at Livermore called NIF, N-I-F, that's doing that. I think they're building one like that in France. Anyway, that plasma, after it's all compressed, is about the density of water, way, way denser than air. And of course, the interior of the sun is a plasma, but that's as dense as metal, the density of lead or something like that. But why is it a plasma if it's that dense? Because it's ionized. There are no neutral particles in there. It's just positive and negative charges really closely packed together, right? And very, very hot. Middle of the sun's 12 million degrees, okay? And it's in the plasma state. So essentially a plasma can have any kind of density you can imagine. For example, a plasma that surrounds the Earth, which our satellites fly through, for example, is very, very tenuous, much less dense than this. There are only hundreds of particles per cubic centimeter, okay? And way, way, way out, I mean, the whole universe is filled with plasma. There are enormous clouds of it between galaxies and so on. And there the densities could be 1 particle or 2 particles per cubic meter, right? You could say, well, that's nothing at all. You know, in a room this size, there'd be maybe 50 particles. But remember that these plasmas are light years across, all right? So when you count up all the particles, there's a lot of them, and there's enough of them there, whoops, to have all kinds of plasma phenomena occurring, okay? So there's a lot of astrophysical uses of plasma too. Any more questions? Okay, I can show another picture. This one. All right, this is data taken from an experiment we did some years ago. It's also pretty. It's a composite. So these gray things we drew in, these cylinders, and they are made to size of, they're cylinders of carbon. And so what we had was 2 intense laser beams coming, one just missing this and hitting that, the other one coming in from the side, just missing that and hitting this. And when they hit the target, the laser is so intense that a dense plasma comes off. And these 2 dense plasmas move toward each other. There's a background magnetic field, very strong, going in and out of the picture. But the plasmas are so dense, they just cross it. And these 2 pictures, this is actually a photograph, this pink stuff in here, taken with a fast camera. It had an exposure time of 3 billionths of a second. And it took this picture about 400 nanoseconds or so. I don't remember the exact number. 400 billionths of a second after the targets were struck. And these 2 things collide. And then what happens is these plasma, this gives birth to a wave, a magnetic wave. It's called an Alfvén wave. And these green things in red are field lines, magnetic field lines of the wave. Maybe I have a picture of the wave in 3 dimensions. You know what? I'm going to put my glasses on so I can see what I'm doing. Let's see if I have it. Actually, I didn't put it up. Well, here, this will work. So again, this is looking from the opposite direction. So here's this target, which we drew in, but the rest is data. These are 3-dimensional electrical currents of that wave that I just showed you, this Alfvén wave. And she saw it yesterday in 3D. It's really 3-dimensional. These things go corkscrewing. And you could see here the currents, all currents have to close. They can't just end in space. Like here, this ends, but it's only because we stopped following it over there. All currents have to close, and you could see this one closing. It's coming along like this. It's going under here, doing this convoluted path, and then back the other way, right? So, and this is at 1 instant of time. As time goes on, these are moving and changing, and the currents are coming at us very quickly. So they're moving about 1 million meters per second. That's how fast this thing's moving toward us. But with modern digitizing equipment, there's no problem at all capturing it. So the advances, I've been in this field, I've been at UCLA for 46 or 7 years. And so when I was in graduate school or just started here, the kind of data that you're seeing now and the digitizers we use were unheard of, right? When I was in graduate school, our school bought the first computer, which I learned to program, and you had to use punch cards. And now your cell phone is probably 1,000 times more powerful than that computer, which filled the whole room in our computer center when I was in grad school. And so saying that, oh, I have a USB disk with 16 gigabytes would be the same thing as saying, guess what? I just learned how to fly or something like that. Totally unthinkable. But now the kind of progress in electronics, computers, everything is astounding. And people are doing stuff these days that you couldn't even imagine trying to do 30 years ago. So, and who knows what the future will hold. Hopefully, if there is a future, we will have really, really huge steps more in diagnostics and the ability to build and design machines to study phenomena like this. More questions? Out there? Okay. So I guess wrap up. Why am I in plasma physics? All right. Now, some people go into plasma physics these days because they want to be part of the effort to do thermonuclear fusion and essentially save the world from the climate disaster that we're facing. And so they want to work on fusion devices and get this new source of energy out there. I wasn't like that. I just wanted a decent job. And when I was in college, I took all kinds of courses in the beginning because I really didn't know what I wanted. And when I started taking physics classes in college, I got hooked on physics, right? And so I knew that's what I wanted to do. And I love working with experiments. So I said, okay, I want to do experimental physics. When I got to graduate school, I looked around and you go to various labs and they had different types of experimental physics. And it looked like plasma physics was interesting, but I didn't know much about it at all, really, then. But it looked interesting. And so I said, okay, I'll try this. And I've been happy ever since. So essentially, coming here and working with all that equipment that you saw on this visualization is like being in a toy store for adults, right? It's just you come here, you have fun all day, time goes by, and then suddenly your wife calls and says, why aren't you home for dinner? And you say, oh my goodness, it's 7 o'clock. So that's the kind of job you want eventually, something that's just fun, right? And this is. So that's really why I do it more than anything else. Okay?
Thank you so much. That was amazing.
Hi.
Thank you so much. That was amazing. And
okay.
It's yes, it was wonderful. Thank you.
Sure. Okay, so what's next? Oh, we were going to talk a while, and then I guess she'll come
so
back.
there was one last question was from Ashley. How has it been seeing the field develop over the years?
How, pardon? How, what?
A question from Ashley. Let me just send it. How is it to watch the field develop over the years, the plasma field?
Oh, it's amazing. It's blown up exponentially. As I said when I was talking, that the kind of diagnostic equipment we can buy and the kind of electronics available, some of the stuff we build ourselves, has changed in ways that were unimaginable over the years. And of course, you know, things go up and down. All our funding comes from the government. So, as I said, DOE and NSF. We've also gotten funding from the Air Force and Navy. We're not building planes or ships, but they're interested in what we do. And so, except, you know, the funding goes up and down. It's very mercurial. So there'll be really lean years and then there'll be great years. And of course, that affects us greatly. But it's the same, I guess, with education everywhere. So we're at the mercy of politicians, and some of them are anti-science and some of them are pro-science, and you just hope for the best. But we have little control over that. Of course, we're always asked to be on government panels and so on, and lengthy position papers are written and generally ignored.
Well, there you go. On that note, we will say goodbye to you. And once again, thank you so much for your generosity, for your creativity, inspiration. And we hope to finally get somebody to give us some funding to do amazing art science collaborative
Yeah, we'd
work.
love to do science and art project. And,
we would love that. Yes.
Yeah,
thank
we
you.
would too. And it would be great to work with you without masks in the future when this whole stupid virus is gone.
That's right.
So,
let's hope for
all right,
the best.
take care.
All right, bye.
Bye-bye.